For our fourth set of notes, we have symmetry, and we're going to talk about line symmetry and rotational symmetry. So that's why it's in this section, because we're talking about this rotational symmetry, and we have lines of reflection, and that's where this line of symmetry is coming in. So the line of symmetry is a figure that has a line symmetry if the figure can be mapped onto itself by a line of reflection. So you can think of a mirror image, or also when you draw a heart, or when you make a Valentine's heart, you have your piece of paper and you fold it in half, so here's the fold, and you cut it right there, and then when you open it back up, you've got a perfect heart with your crease down the center, and that is a line of symmetry. Or a butterfly would have a line of symmetry down the center of your butterfly. So in each of these figures, we need to name how many lines of symmetry there are. So where can we draw lines? So if we fold the paper, that they will line up exactly on top of each other. On this first one, there's none. So there'd be 0 lines of symmetry. On this next one, we can see that there is only 1 line of symmetry, because if you turn your paper around in a circle and see if you can draw another line through it, you're going to see that it's not exactly perfectly symmetrical on both sides. So this is the only line of symmetry you could draw. Now for this third one, for our triangle, we have 1, 2, 3, so make sure you count them as you go. So even though it looks like there's lots of lines in there, there's really only 3. For a circle, we have infinite numbers of lines of symmetry, because no matter where we draw them, we're always going to be able to find another one. That's the whole point of what a circle is, because it's symmetrical all the way around. Next, we have rotational symmetry. So a figure has rotational symmetry if the figure, that's supposed to be the word figure, not fire, is mapped onto itself by rotating the figure less than 360 degrees. We've got 4 examples again. So this first one is kind of like an hourglass figure, and we want to think of, if we grab it with both sides of our finger and we rotate it around, how many times can you rotate it all the way around in a circle before you land back on itself? This will be the easiest way of figuring out the number of degrees of rotational symmetry. So here we could rotate it once, and that would line on top of itself, and then twice, and we're back to where we started. So if we take 360 and we divide it by those number of times, that gives us 90 degrees. So we have a 90-degree rotational symmetry for that first picture. This next one, we could rotate 1, 2, 3 times around. So 360 divided by 3 times around evenly gives us 120 degrees. Do the same thing with our star. If we start here, we can rotate it a little bit. That's 1, 2, 3, 4, 5 times around. So 360 divided by 5 gives me 72 degrees of rotational symmetry. So we can turn it just 72 degrees, and all the points will line back up on top of itself. For this last one with our smiley face is a little tricky, just because it's a smiley face. You would think that because it's a circle that you could rotate it infinitely many of times for it to land on top of itself, but the fact that there's a picture drawn inside of it, there's only one way that that face will end up lining up exactly the same way, and that's if we turn it around 360 degrees, and we need it to be less than 360 degrees, so there's no rotational symmetry at all. For each of these questions, we are going to figure out, does it have line symmetry? If it does, how many? And we are also going to figure out if there's rotational symmetry, and if so, what are the degrees of rotational symmetry? For number 1, I'm going to do my line symmetry in pink. So we've got 1, 2, 3, and then we could also go through the points as well. So that would be 4, 5, 6. So there'd be 6 lines of symmetry. For our rotational symmetry, we could start with any of the points, and we could rotate it just a little bit and they'll line on top of itself again. So that'd be 1, 2, 3, 4, 5, 6 times around. Remember, we have to take 360 then divided by those 6 times around, and that gives us 60 degrees of rotational symmetry. On to number 2. So for number 2, the lines of symmetry, are there any ways we can draw any lines through it? We might think down the center, but then both the sides don't have these little zigzags the same way. We definitely can't go this direction, so there'd be no lines of symmetry for number 2. Rotational symmetry, kind of for the same reason, this is a very identifying mark right here, so if we turn it around, it'd have to turn around all the way in 360 degrees before it would line on top of itself again. And it has to be less than 360 degrees, so there would be no rotational symmetry for number 2. Number 3, I would like you now to tell me the line symmetry for number 3. You should have said that there is one line of symmetry. Now for the rotational symmetry, I want you to do that one as well. For the rotational symmetry, since this is an A, if we rotate it around, that would be upside down A, so it would have to be exactly the same way around, and that would be 360 degrees, and then we have no rotational symmetry. For number 4, we have a right triangle, and we can see that our two sides are not exactly the same, so the two legs are not identical, they're not congruent to each other, so it's very obvious that we'd have to rotate it all the way around. That's the only way that we'll have the same triangle lined up exactly the same. So there would be no rotational symmetry, just like previously, and there's no way for us to draw a line going through our triangle anywhere so that all of the sides and angles will match up together. So there's also no line symmetry. These last two have a little more character to them. So on number 5, it's kind of like what we had up here for our hexagon that we had. And we definitely have these different points, and our snowflake is symmetrical on both sides. So we can draw lines through. Let's go for our points first. That would be 1, 2, 3, and then we can draw it right down the center that they line up together. So that'd be 4, 5, and 6. So as long as the design inside is also the same, we're going to have 6 lines of symmetry like we did for number 1. For the rotational symmetry, it will be something similar. If we start on one of our points and we go around, we have 1, 2, 3, 4, 5, 6 times around. That means it would take 6 turns before our figure would line exactly back on top of itself where it started from, but it does line up with each of those 6 times we turn it around, and we would have 60 degrees of rotational symmetry again. Number 6, for our line symmetry, if we think of dividing it down the center and fold this over, it won't line up exactly with this one. We can't do it diagonally because the curls are not facing the same direction, so there's no line symmetry. For the rotational symmetry, I want you now to do this one yourself. So your rotational symmetry, you will notice that if you turn your, we can call this like a little bow tie, if we turn it halfway around, it does line up with each other, so the curl will be facing the right direction, and then it would take 2 turns before it lines it back up where it was to begin with. So there's 2 turns in there, so 360 divided by 2 gives you 180 degrees of rotational symmetry.